Hello everybody, I'd like to look at some quadratic functions. Um, Let me write the function f of x in its most general form. So we've got a function f of x, well, a quadratic function f of x is ax squared plus bx plus c. Now just to note, a is not 0, because if a is 0, then we just have a linear function. And we're not interested at the moment in looking at the linear function. Also, x is real, so we're only dealing with real polynomials here. So the first thing we can immediately deduce from this, when you have a polynomial p of x is equal to p naught plus p1x plus p2 x squared plus all the way to, let's say, pn x to the n. There are n roots. Oh, I wrote that quite untidily there. Sorry about that. There are n roots. So what this means is there are n solutions for x that satisfy the equation p of x is equal to 0. So there are n solutions. So now, since the quadratic function has degree 2, its highest power is 2, there should be 2 solutions. So a quadratic function has 2 roots. That means there are 2 occasions where the x-axis gets intercepted. So let's imagine something like this. This is very general, I'm just trying to build intuition here. So you've got your y-axis and your x-axis. And here's our origin. So let's say we had 2 roots. Let's call the one, I'll just call it R1, and the other one R2. So that means this graph, this quadratic graph, is going to cut the x-axis at 2 places, at R1 and R2. Now, just to gain some intuition, let's think about this. Let's imagine, we have no idea what this thing looks like, but let's imagine this function is increasing and it cuts R1. So it cuts the x-axis over here and it's increasing. But now we don't know what happens, we don't know the shape, but at some point it cuts R2. This is a continuous connected function, so if it's going to cut R2 at some point, it has to be going downward. Because if it continued increasing, it would just go higher and higher and higher all the way. So in order for it to cut the x-axis again, at some point it has to be going down. So at some point it has to be decreasing. And what we will find is that in order for this to be possible, there's going to be a point somewhere where this function changes from an increasing function to a decreasing function. And that point where it changes, let's say it changes over there somewhere, there'll be a point over there that will have an x value and a corresponding y value. That point we often call the turning point. No, I'm writing quite untidily, I don't know what's going on here. Turning point. Okay, need to deal with this. And more generally, it will be a stationary point. I think we should just, okay, stationary point, yeah. So when you're dealing with a quadratic function, find the roots, find the y-intercept, I suppose, and then we want to get that turning point. Using the same intuition, let me try again, but this time with starting from decreasing. So using a similar argument, got the x, got y. Let's imagine this is root 1, this is root 2. Let's imagine that this function was decreasing when it cut the x-axis there. So it was decreasing. In order for it to cut the x-axis again, it will have to at some point change direction. Yeah, it's increasing. Once again, like I said, we don't know where this is. We haven't solved it yet. But somewhere here, there's a turning point. And what's interesting about the quadratic function is that this turning point also happens to be the axis of symmetry, which is often called the vertex. The vertex. And it's an axis of symmetry. And whatever that x value is there, that this line is just x is equal to that particular number, that particular value. So x will be equal to the value of x at the turning point. So this already gives us some sort of a recipe, shall we say. When you have a quadratic function, so to sketch, let's say to sketch the quadratic function, or let me say to sketch the graph of a quadratic polynomial. Quadratic polynomial. We'll just do the basic stuff. So the first thing is find the roots. Find the y-intercept. Find the y-intercept. And then I suppose find the turning point. There'll only be one turning point. Find the turning point. And I will put in the other terms here, or stationary point. And because it's this particular graph, it's also the vertex, or the axis of symmetry, but you know what, let's just leave it like this for now. So let's look at an example, and the best way to learn is just to use an example. So I'm gonna take just gonna take an example that I can find here. Let's just go with something like this. So f of x is equal to 2x squared plus x minus 3. Now, to get the roots, we say f of x is equal to 0, and then we solve for x. Now, we can immediately just use the quadratic formula, plus or minus b squared minus 4ac all over 2a, and then we can get two values for x. This is legitimate and this is perfectly fine. So we could use the quadratic formula and we'll get the correct solutions, but I think in this example we can probably factorize. So let's just see. So we've got 2x squared plus x minus 3 is equal to 0. So let's see now. 2 is a prime number, so we'll have 2x multiplied by x. But now we need to figure out what these other terms are going to be. So we've got negative 3 here. So the factors of negative 3 are 1 and negative 3, or negative 1 and 3. And we make sure that they expand out in such a way that the middle term is positive 1x. So the way to do that, and I mean this comes with practice and playing around with factorizing. So we'd want the 2 to multiply with the 1, and the 1x to multiply with 3. And then what signs do we have? Well, our middle term here is positive 1. So we need the 3 here to be positive and the 1 to be negative. And let's just do a quick test and see if we get the right answer. If we expand 2x plus 3 times x minus 1, what do we get? 2x times x is 2x squared. 2x times negative 1 is negative 2x. 3 times x is positive 3x. Positive 3 times negative 1 is negative 3. And if you look here, negative 2x plus positive 3x gives us positive x. So this is correct. So we've expanded it correct. So we can get our roots here. So we've got 2x plus 3 is equal to 0. And the other root is x minus 1 is equal to 0. So we can solve here. 2x is negative 3. And this means x is negative 3 over 2. And if you want to write it in decimal, this is just negative 1.5. And on this side, x is 1. So we've got our roots. Our roots are x is negative 1.5 and x is 1. And the roots also means x-intercepts. Okay, so we've got this part, so we're happy. But we're not completely happy. So let's see what the y-intercept is. So to get the y-intercept, we will set x to 0. So to get the y-intercept, we calculate f of 0. So f of 0 is 2 times 0 squared plus 0 minus 3, and this is just minus 3. So the y-intercept is at minus 3. So the point, of course, will be 0 and minus 3. Because the y-intercept, if you want to be specific here, even with the roots, the actual points will be, let me just write them here. Because the x-intercept means y is 0, so the actual points will be negative 1.5 and 0. And the other point will be 1 and 0. Remember, we always write x before y. And then for the y-intercept, the x value is 0. And then the y-intercept, the y value is negative 3. Now, let's do the third one and find the turning point, or the stationary point. Now, if we were using calculus, it would be straightforward. We'll just get the first derivative and set it to 0 and solve for x. But I'm not going to use calculus here. I'm going to use a bit of a geometric argument. And the geometric argument is that, I'm going to draw it a little bit small here. So if we've got, and this, please note, this is only applying to the quadratic function. If we've got our Cartesian plane with x and y, if we've got root 1 and root 2, and let's just say we knew the shape, it goes something like this. The distance here between root 1 and root 2. So these points would be R1 and 0. Because it's 0 on the y-axis. and this point here would be R2 and 0. The midpoint, halfway between these two roots, is where you will find your axis of symmetry. So to find the turning point, or the x value of the turning point, we want the midpoint between the two roots. So let me see how I can word this. The axis of symmetry, remember there's so many ways to describe these things. So the axis of symmetry is at the x value that lies in the midpoint, or at the midpoint. Let's say lies at the midpoint of the line that joins the two roots. Or let's not say the roots, the two x-intercepts. So let's call it, I don't know, TP for turning point would be equal to a half times R2 plus R1. This is just the midpoint formula. It's just the midpoint. If you do analytical geometry, this is just the midpoint formula of a line, of a straight line. So we can find the midpoint like that. And in a very general sense, we know our two roots from the quadratic formula. X is negative b plus or minus the square root of b squared minus 4ac all over 2a. There's two solutions here, the plus and the minus. So let root 1 be negative b minus square root of b squared minus 4ac. I'm doing this now very generally, so we're using a, b, and c as just dummy variables here. And let R2 be negative b plus b squared, square root of b squared minus 4ac all over 2a. So if we want the midpoint of this, let's see what happens. So I'm going to again just say xtp for turning point. It's going to be half of R1 plus R2. And if we plug this in, I'm going to make square brackets here. We're going to have negative b, so this is R1, negative b, negative square root of b squared minus 4ac. All this is in the square root over 2a plus negative b plus square root b squared minus 4ac under the square root all over 2a. So let's do a little bit of simplification. We've got the same common denominator, so we can just add them, just continuing here. So this is equal to a half. Let's put it all under one denominator. So we've got negative b minus the square root of b squared minus 4ac minus b plus square root b squared minus 4ac, and all of this is over 2a. Now what we can see very nicely is that the square roots, there's a negative on this one and a positive on this one, so they cancel out. And upon further simplification, we end up with a half, and then negative b minus b is negative 2b over 2a the 2's cancel here, and then we're left with negative b over 2a. And this is quite a remarkable result, because this is telling us that if you are given a function f of x is equal to ax squared plus bx plus c, the turning point, or the axis, well, the axis of symmetry, or the x value of your turning point, can be immediately taken here as negative b over 2a. And here's another reason why I notice a can never be 0, because of course you can never divide by 0. Now please remember, this only gives us the x value, so we must always remember to calculate the y value as well. So the y value of the turning point, I'll just call it ytp, we get by plugging in the x value into the function. So first of all, what is the x value here? So let me just do this. X tp for our example. Remember, our example was 2x squared plus x minus 3. So the b, so it's obviously negative, and then the b was positive 1, and a is 2, but of course it's 2 times 2 here. So the x value for our turning point is negative 1 over 4. Again, if you want to write it in decimal, it's negative 0.25. Now we must plug this value into our function. So it's 2x squared, but x, of course, is negative a quarter, all squared, plus negative a quarter minus 3, and this is equal to, let's just do it the long way, it's 1 over 16 minus 1 over 4 minus 3. Okay, 2 times 1 over 16 is just 1 over 8 minus 1 over 4 minus 3. Let's just put all this under one common denominator. Let 8 be the common denominator. So we end up with 1 minus 2 minus 24. This is just arithmetic of fractions. And 1 minus 2 is minus 1, minus 24 is minus 25 over 8. I'm going to keep it in fraction form, but this is about 3 point something. So to be very exact, I mean, this is negative 3.125, because it's 3 and 1/8. So I can say, therefore, turning point is at x is equal to negative a quarter. Yeah, negative a quarter, just double checking. And the y value is negative 3 and 1/8. So we can actually sketch this. So let's do it. We know what our roots are. We know what our y-intercept is. We've got very little to fear. So there's y, there's x. Our y-intercept, let me just make the origin there. The y-intercept was at negative 3, 0, negative 3. So this is on the y-axis. Our x-intercept was negative 1.5 and 1. Let me just double check that. Let me go further up here. Yes, negative 1.5 and 1. So let's make it a bit bigger. So we'll put the 1 here. And then negative 1.5 will be about there. And our turning point is when x is negative a quarter, so just about somewhere here. Let's put it there maybe. So that's negative 0.25. And the y value is negative 3.125, so it's just underneath here, it's about here. This is where the function turns. So when we sketch it, we know it must go through the roots, the x-intercepts basically, must go through the y-intercept, and it must go through the turning point. So we'll have something like this. And then try not to make it V to V like, just try to show that it does turn. And this is what our function will look like. And well, this is our f of x is equal to 2x squared plus x minus 3. And that's enough for this video, so thank you guys. Bye bye.